Welcome to Module 3, Secure Application Design and Architecture. Our objectives in this module are first and foremost to make sure you understand the importance of secure application design. We're going to look at various design principles. We're going to talk in depth about threat modeling. We mentioned that briefly in a previous module, but in this module we're going to get into a lot more depth on that topic. In fact, we're going to describe the entire threat modeling process. We're going to look at two modeling techniques, STRIDE and DREAD, which are acronyms for models that help you understand threat modeling. And finally, we'll describe secure application architecture design. This is a quote: "Most of the web applications are vulnerable due to insecure design of applications at design phase." Now the concept here is, again, something you've already heard in previous modules. It's ineffective and inefficient to simply try to tack security on at the end. We need to do it from the beginning. In the last module we discussed requirements. Now we're going to take that into the design phase. Another quote, and this comes from the PHP Security Consortium: "Secure programming cannot make up for a poor design. This is much like building a building, a home, or an office. If the design itself is flawed, quality work done after the fact is not going to make up for that flawed design." Now here you see a chart that basically describes different phases of the software development lifecycle and how much it would cost to fix a vulnerability. And basically, if you wait till testing, it's 15 times the cost of fixing that problem in design, and if you wait till deployment, it can be 100 times or more the cost of fixing something in design. That alone should definitely emphasize the importance of secure design. First of all, any sort of negligence in security at design and architecture phase is not only going to lead to vulnerabilities, obviously, but it may lead to vulnerabilities that are difficult to even detect in production, and they'll definitely be expensive to fix. Security vigilance, the opposite of negligence at design phase, enables you to detect potential flaws early enough that they can be corrected before they've caused any significant issues. Now, of course, the secure design is predicated on good security requirements, which we discussed in the previous module. Secure design can be a challenging process. You need to design required security controls in such a way that they interface well with business functionality requirements. It's entirely possible, particularly if the requirements weren't done well, that the security requirements may conflict with the business requirements. So we need to make sure that we sort out those conflicts. You need to identify the threats in sufficient enough details that developers can code. Put another way, abstractly and vaguely discussing web vulnerabilities is not going to help a programmer to mitigate those. Now, if you specifically identify SQL injection involves typing in non-standard symbols into a text box, well, that's something a developer can work with. They can write code to filter out that sort of thing. Designing architectures in such a way that it mitigates as much threat as possible. In other words, the fundamental structure of your application is done in a secure fashion. That's going to facilitate secure coding. And then, of course, you have to enforce those secure design principles and force developers to think about security throughout their entire coding process. So let's look at some actions that take place during secure design. We start with looking at the security requirement specifications that we got from the requirements phase that we discussed in the previous module. Now we do some threat modeling. Let's look at what our threats are, and we're going to discuss this in some detail during this module. And let's then add to that any secure coding standards that we need to be implementing. We've discussed a few as we've gone through these modules. We'll see more as we go further. And that's going to lead us to a place where we can design secure application architectures. So secure design principles are basically practices or guidelines that should be enforced on developers so that they're following secure development processes throughout their entire development phase. This helps in deriving a good, secure architectural layout from good architectural design and decisions. This helps you eliminate any architectural flaws. Now let's think about this for just a moment. The architect of your application is going to be the structure, including code modules you reference, libraries you use, class diagrams, things of that nature. That structure needs to be set up in a way to most enhance security. There are several principles in secure design. Now, some of these are very, very good. Some of these are less effective. The first one you see on this list, security through obscurity. Now, you may have heard that derided throughout the security community. And by itself, it would be very bad security. But obscuring some things, in addition to taking other steps, is always a good idea. Now, you can see the list on the screen, so I won't read each and every one to you, but let me hit some of the most important ones. Secure the weakest link. Doesn't matter if your application has dramatically robust security throughout. If an attacker can exploit one weak link, the other parts really weren't important. Use the least privileges principle. You're going to hear me talk about this throughout this module and in other places throughout this course. Least privileges means that any user, any system, any service, any process only has just enough privileges to accomplish their job tasks and no more. Fail securely. Now, this is different than in physical security. In physical security, for example, doors are supposed to fail open so you don't accidentally trap people inside should there be a fire or something of that nature. Well, software isn't like that. Failure should lock down. It should fail securely. Do not trust user input. That should be just paramount in your mind. Keep security simple. Now, what this means is end users can easily do what you need them to do. If it's too complicated, they just won't do it, or they'll find ways around it. Fix security issues correctly. We don't want to put a Band-Aid or a patch on something that is itself insecure. We want to make sure that our repairs, our corrections, are done properly. You're going to hear a lot in this lesson about fault tolerance, fault detection, fault removal, and fault avoidance. These are just a few of the secure design principles we're going to be discussing in this module. Let's start with the security through obscurity. Basically, this means people can't find the security issue. Now, if that's all you have, you really don't have security, because we have to assume that a dedicated attacker will eventually uncover the vulnerability. However, preventing access to certain users to protect internal data can be a good idea. Let's assume, for example, you were developing an electronic medical records application. One very secure part of that would be the prescription writer. Now, by law, physicians, physician's assistants, and nurse practitioners are the only people who should be able to legally write a prescription. Therefore, using security through obscurity, you might have, for any other user that logs on, they don't even see a prescription writer button. Now, that wouldn't be your only security, because presumably someone might eventually uncover that functionality, and they might log in and write a script they shouldn't. But we also use security through obscurity to prevent them from even trying. If you couple that with other things, like in my example, you couple it with strong authentication and auditing, then you've got a really good security mechanism. Put another way, you've heard security through obscurity is not security. And by itself, that's true. But as an additional measure to further obfuscate targets, coupled with many other security measures, it's actually a good idea. Securing the weakest link. Attackers just want in, and they don't really care how they got in. So if you have tremendous security in 90% of your application, it's that 10% they're going to attack. So one of the things you have to do, even during the design phase, is look for the weaknesses are. Any point where a system connects with another system, any point where there's any sort of external communications, be it Wi-Fi, cellular, Bluetooth, doesn't matter. Any point where you have to interface with any code libraries, any point where you have to read in data, any point where you take in user input, all of those are potentially weak links. And direct your attention there during the design phase, you're going to have a far more robust application. We mentioned the least privileges principle, and this may be one of the most fundamental concepts in all of security, not just secure programming. Now, some people get upset by this. They think, what, you don't trust me? Why can't I have access to that data? It always comes down to one simple thing. What do your job requirements entail? And that's all you get access to. It's not a matter of trust. It's not a matter of evaluating your skill. But you don't need access to it. Now, the place I see this misused the most often is with services. Consider your database server. Maybe you're using Microsoft SQL Server and you've installed it, and just to make it easy, you installed it as an administrator, or maybe even part of the domain admins group. That database service does not need domain admin privileges to execute the database. You've just given it more privileges than it needs. And if I can attack your system and gain control of that database service, I can do all kinds of terrible things now that I could not have done if you had simply run least privileges. Secure by default is another concept we saw in the earlier slide. The software or application or system or whatever it is should have security enabled by default. It should not be that the thing is unsecure by default and they can optionally add security. Security, things like passwords, password complexity, password aging, those are just examples, but those should be on by default. Now, there may be scenarios where you allow an administrator to override that, but the default should always be secure. Failing securely. If something shuts down, it should make sure that everything gets turned off and closed in the process. If there's error handling, that's an application crash, close database connections, close password files, re-encrypt data that's been decrypted, things of that nature. Fail securely. Another important thing that's also true in network security as well as application security is defense in depth. Let's go back to my electronic medical records example. It's not good enough that you have strong authentication at the initial login, but what about the individual functionality within the application? Because you have a wide range of users that access this, front desk personnel, nurses, physicians, billing personnel, all kinds of things. They have different levels of access. So there should be different levels of security throughout the application. It should never be the case that once I get in the front door that the rest is wide open to me. And something I said I'm going to say again and again, and you'll maybe get sick of hearing it, do not trust user input. You always examine and filter input. It could be intentionally malicious input, or it could be simply an error. How often have you yourself mistyped something into a text field? Well, that could potentially be a problem. So we always are suspicious of any input. The only thing I would add to this is don't only mistrust user input and validate and verify it, but validate and verify any input from any source. If you're reading data in from a database, don't assume that's safe. Validate it before you use it. If you're reading data in from a web service, don't assume it's safe. Validate it before you use it. The attack surface. All the different ways someone can attack your system. Now, obviously, you cannot have a zero attack surface because if you did, no one can use your system. Think about that for a moment. Any way that an end user can interact with your system is potentially an attack vector. So all we're saying here is we need to reduce that attack surface. If there are any extraneous entry points that you don't really need, get rid of them. If there are any features or protocols or functions that you don't really use, turn it off. Anything that you can do to reduce the attack surface without reducing functionality is preferable, and you should explore that option. As much auditing and logging as possible. Now, this goes beyond just secure programming to simply good programming. I'm sure you can relate to the situation wherein a program has a bug. You're trying to find out what the bug is, but the logging from the system is insufficient for you to determine what happened. Well, in security scenarios, that situation is simply multiplied and magnified. So what you want to ensure is that you have sufficient auditing and logging that in the event of a security breach, you can determine exactly who did what and how they did it. Keep security simple. The harder it is to understand, the harder it is to implement, the less likely it is going to be that the users do it. Even technical users. You like ease of use in your products, and so do your end users. So if security is overly complex, people just aren't going to do it. That's another reason that biometric authentication is becoming so popular. It doesn't require any complex actions on the part of the user. They just have to be there and to have a fingerprint or an eye scan or something of that nature. Separation of duties. Separation of duties means if there's a critical process that could cause significant damage, no single person can do it. Let's continue with our electronic medical records example. There could be a scenario in which a patient's record legally and legitimately needs to be changed. The nurse recorded the wrong blood pressure. We later realized didn't need to change it. But changing a record, it's a very serious thing. It could be part of fraud, could be part of covering up malpractice. So changing a record should require two users, one to do the change and one to then later authorize and approve that change. That's just one example of a separation of duties. No one person can do everything required for a particularly critical task. Now, obviously, you can't do that on every activity. It would make a system very un-user-friendly. But on critical things, you should consider separation of duties. Fixing security issues correctly. So, you have a situation where users can accidentally view another user's account balance just by adjusting a cookie. Well, how are we going to fix that? Well, you could make some minor change that handles how they're going to handle a cookie, and it's okay for now, but it in turn either introduces another problem or can itself be circumvented again. So we need to make sure when we have a security issue and are rushed to patch it, make sure that we slow down and we patch it properly. One of the key parts of this module is applying security in the design phase. When you're designing all your interface diagrams and use case diagrams and flow charts and class diagrams, whatever design methodologies you use, security needs to be a part of all of that. Make sure you protect sensitive data. Now, I'm happy to say that hard coding of sensitive data I don't see so much anymore. 20 years ago it was quite common. Today that is far less common, but that's just a terribly obvious example of protecting sensitive data. As we're going to see later in a later module, .NET has a rich set of cryptographic utilities built into it. You don't even have to know much about cryptography to use them. So let's make sure that we are using these to encrypt sensitive data. Exception handling. Now, we have an entire lesson on exception handling. That's how important it is. But anything that could cause an exception or error needs to not just be blocked, but handled properly. Why did we have that error? What caused it? Is there something we need to change? Is there some notification we need to give an end user? What do we do to handle this? Now, memory management is actually far easier in .NET. .NET does a lot of that for you. But if you're doing any sort of memory management yourself where you manipulate things, you need to ensure that you're doing this well, preventing buffer overflow attacks and things of that nature. Any memory or storage secrets, anything that could wind up in a dump that someone might get of system memory. For example, if a password is loaded into memory, I can forensically dump the memory of that computer and see the password. So if we're going to put something in memory, let's make it encrypted and decrypt it only as needed. Make sure that we delete things securely. All sorts of steps we can take to ensure that we've protected memory or storage secrets. Now, control granularity. This granularity concept we've seen before. It basically means we're getting down to a very low or granular level. We're looking at things with a high level of specificity. Now, applications managing sensitive data should possess privacy protection that can be achieved through flow control. And that means we're preventing data from non-secure information flows. Data has to go from point A to point B to be usable, but what process does it take to get there? Systems with low-level granularity may lack control in protecting data from misuse. In other words, the more fine-tuned the process is, the more fine-tuned the security has to be. If we have a high-level security approach to a low-level granular data flow, we're probably missing something there. And that missing something is part of the attack surface that might expose our data. Different granularity is needed to control information flows within an application. A common way to approach access control is what's called role-based access control, where people are given access based on a role. And this can be done in multiple levels, which is called in-level role-based access control. So you have access to this data at this level, but perhaps not at some other level. Fault tolerance. You have to understand that faults will occur. Does your system completely crash in the event of a fault? Let's say that my system, as one of its ancillary functions, gets stock data from a web service. What if it tries to access the web service and that service is not available, or there's a network connectivity issue? Does that propagate and cause my program to collapse? Or does it simply give a friendly user message that says, I'm sorry, that data is not available at this time, and everything else continues to function? That's the key to fault tolerance. Now, of course, we want to detect faults, and if at all possible, we want to remove them, and that's best done during the design phase. As we carefully evaluate our design strategy and decisions, we may discover faults in the design we can remove. That's wonderful, but fault tolerance is simply accepting the fact that we might not detect or remove all the faults. Now, fault avoidance is another process we can use. Basically, during the development process, we want to do what's called defensive programming. Defensive programming is all about minimizing errors, minimizing safety-critical code, using all sorts of techniques as if we were under attack, thus the term defensive programming. Loose coupling. Basically, things operate independently, and that's called loosely coupled. And the reason that's preferable is if one thing fails, the other thing does not fail. Let's consider my medical application again. And let's say it has a piece of functionality that can send a prescription directly to a pharmacy service. That's a common thing these days. Well, if those two processes are tightly coupled and the pharmacy service is inoperable for some reason, I may not be able to do any prescription writing. I may have other functions that don't work. But if the two processes are loosely coupled and one is failing, the other will still function normally. That's the benefit of loosely coupling. Now, web services and service-oriented architecture are loosely coupled architecture. Platform-independent messages that go back and forth, so they're not tied to a specific platform. Well-defined interfaces that are clearly separated and they're constrained. Messages that don't depend on stateless messaging. These are all techniques that create loose coupling. Human-readable strings for service and instance addresses so someone can see where that service came from. Any of these things, asynchronous exchange patterns, all of these things will facilitate loose coupling. Now, what about high cohesion, which is kind of the opposite of loose coupling? Sometimes I have procedures that work together to form a single function. Well, in that case, they cannot be loosely coupled. Cohesion is basically a measurement of the extent of how related functionalities are in the source code. So a class is said to have high cohesion if the methods in that class perform similar actions in many aspects. This sort of high cohesively code increases readability and reusability without increasing complexity. In other words, I have a class that's pretty much dedicated to one set of functions. There aren't a whole bunch of other things in there. So back to my medical example. I have a class and its whole job is to represent a particular medication. It has properties such as dosage, frequency, contraindications. It has methods like refill, order prescription, but that's all it has. It doesn't have extraneous methods like send x-rays, review CAT scans, because those aren't related to prescription. And because I made it so highly cohesive, I can take this class out and drop it into another piece of code that I might need that just needs that functionality. Change management and version control. I fully sympathize with most web developers in particular who hate change management. Because one of the things you're thinking is, look, this is a tiny change. I could go over and make this little change and it's not a problem. the process of change management will delay me many days for something I could do in 5 minutes. The problem is you cannot be certain what other areas your change will impact or what other changes are being done by other developers. That's why we need a strictly controlled change management process. Although it may seem wasteful, in the end, good, strict change management prevents so many problems. And controlling versions. What if you do accidentally introduce a change that causes some significant problem, and it may take a while to identify and fix that problem? Wouldn't it be great if you could just roll back to the immediately previous known good working version, deploy that while you're working to fix this problem? That all depends on good change management and very well-controlled version control. Now that we've given you some general concepts, let's take a look at threat modeling. I like this quote. It's not possible to design and develop a secure application until you know your threats. What are you trying to protect against? Consider homeowners insurance. If you live in a coastal area, you probably are very concerned with flood insurance. On the other hand, if you live in the middle of a desert where the nearest open body of water is 500 miles away, that's probably not a concern to you. Different threats, different threat modeling, different threat mitigation strategies. It's exactly the same thing with programming. Threat modeling, we first identify what our threats are. Then we analyze and mitigate them. It has to be a structured process. It's not just ad hoc spitballing ideas. It's a structured process, and we also have to rate the threats. How serious is this threat? And there are several criteria that go into that, which we'll see in a little while. This is always done at least at the design phase, sometimes even earlier, to make sure we have good, secure programming throughout the development lifecycle. It can be an iterative process. It may not be a one-time thing. You might cycle through your threat modeling multiple times until you have a good threat model. And the output of a threat model is a good threat model that exposes all the possible threats and vulnerabilities. So let's look at a few things. Start with attack surface evaluation. You look at your application and you enumerate every single entry point and look at them from the perspective of a bad actor. What will they do with these entry points? Now we identify each entry point against all potential threats to that entry point. They're not all the same. Not every entry point is vulnerable to the same threats. The next is really important, impact analysis. Now you might think, any threat's bad, I'm going to stop it. Not necessarily. My own website, for example, has very little in the way of security because there's no database, there's no login, there's no private information. The only things there are data that I freely give away to anyone who wants them. So the impact from someone hacking into my website would merely be to perhaps post an embarrassing picture that I would take down in a few minutes. There's no major impact. So we need to do an impact analysis. How bad is it if this threat is realized? And from all of that, you can now make control recommendations. What are the security controls that will mitigate that impact, that will mitigate that threat? And this is a cyclic process. Once you've identified security objectives, you look at your application, you decompose it to entry points, you identify threats, you identify vulnerabilities. Well, that could also feed into the next cycle of the same thing again, identifying additional objectives, things of that nature. So to create a threat model for an application, you need to have the objectives. Now, of course, you could say the objectives are to be totally secure, but that's not realistic and it's not necessary. I already said previously that security and usability are in conflict. So you have to find the right balance. And that depends on the nature of your threats, the nature of the data you're protecting, your assets. All of those things feed into how much security you really, really need. These security objectives that you formulate are the goals and the constraints that help you maintain confidentiality, integrity, and availability of the application and all of its data. These security objectives should be a subset of the application's functional objectives. In other words, yes, they're separate from the functional objectives, but they have to be met as well as the functional objectives in order for the application to be successfully completed. With these security objectives clearly defined, you can now identify which things need the most attention and which things can be maybe given a little less attention based on impact and probability. You can start with questionnaires, and here on the screen you see some sample questionnaires, and based on the answers, that leads us directly to specific security objectives. Now, questionnaires are only one of your tools. There's, of course, the storyboarding and brainstorming sessions that we looked at during the requirements module. Give yourself an overview of the entire application. What are the users? How will they interact with the system? What are the use case scenarios? What technologies will be used? What are all the interface points? What are all the data input and output points? This gives you a complete view of your application, for which you can now identify application security mechanisms. Diagram the end-to-end deployment architecture. When you finally deploy this application, what all is involved in that? Now, in the diagram we see here, end users are shown, the back-end SQL Server database is shown, and we can see boundaries set up for trust boundaries to the level of trust you have based on the system you're discussing. And you can see that we have different levels of authentication. To simply get to the web page, anyone can come in, so it's anonymous. To get to the e-commerce portion, where we have forms authentication. For that portion to in turn talk to the database, then we have Windows authentication. So we have different levels of authentication at different parts of the architecture, based again on a threat modeling. Identifying user roles, we're not talking about their corporate roles such as administrator, doctor, nurse. We mean who can do what in that application. And be particularly focused on those users that require higher privileges. They have to have it to do their job. In our medical example, a physician requires a high level of privileges. The front desk person doesn't. But because the physician requires the higher level of privileges, that's a user role that deserves a little more attention in your secure design. This brings us to use case scenarios, which we saw previously. It identifies the functionality and usage of an application based on the various users. Who can create, read, update, and delete? What data can they create, read, update, and delete? Those sorts of issues have to be addressed. Understand completely how the users will interact with the system, how the system will interact with other systems. Identify the technologies used to develop and deploy the application. How are you rolling this thing out there? Now, if it's a web application, obviously you're putting it on a web server. What web server software are you using? Running on what operating system? Communicating with what database? Are there any particular technologies you're going to be using? Adobe Flash, things of that nature. What programming languages do you want to use? Now, although this course is on .NET, there are multiple .NET languages. Are you using VB.NET, C#? What is your preference and why? Identify and highlight the key elements looking at the following application security mechanisms. Now, we don't have to read all of these, you can see them, but notice first is input and data validation. That's always such a fundamental issue that if you haven't accomplished that, it's unlikely the rest are going to be very effective. Look at authorization, identify sensitive data, properly implement cryptography, make sure we have good exception management, make sure you have thorough authentication. Configuration management, you might not have thought about that, but your application has to be configured, the server it's on has to be configured. Are there secure versus insecure ways of doing that? And of course we have the things we've discussed before, such as session management, parameter manipulation, auditing, and logging. When I say decompose the application, you break down every external dependency, every single entry point, every single asset, all trust levels, and perhaps even create data flow diagrams to show how data will be utilized and flow through your application. Now, this is an example of some of the things that you might document with threat modeling. Some of them you have to have, such as application name and version. The number of participants or the reviewer, those are optional depending on your scenario. But we basically want to know what our threat model is, what applications it applies to, and what versions of that application. Here we see an example one, and the description is pretty thorough, and that's the kind of description you want to be aiming for. something that is clear but detailed enough that someone can follow it and get meaningful, actionable information out of it. Those external dependencies, at a minimum, you do depend on the network and the operating system you're connected to. Are there vulnerabilities there that might impact your application? Do you have additional external dependencies? Do you communicate with other services? Do you have files you read and write? Are there deployment issues? For example, if you're deploying on a smartphone application, which smartphone operating system? How will this be vetted? That sort of thing. Will there be a firewall in front of the server? Is the application running on the server or on a separate machine? You've got all kinds of issues here to discuss. Now here's an example of external dependencies for a hypothetical college library website running on Linux Server and Apache. So we look through that and we see what our external dependencies are, what databases we're concerned about, what operating system, and what we could do to try to mitigate threats. Entry points, as we said, is anywhere anyone can get in. Now, obvious examples are data entry forms, admin interfaces, login web pages, operational command and monitoring interfaces, any API, those sorts of things. And here we see an example of how you might identify an entry point. In this case, it's an HTTPS port, and we look at the login page, the login function, and the various related items to this particular entry point. Look at your assets. What data do you have to protect? What about reputation and safety? Depending on the nature of the data, it could devastate your organization's reputation to have a breach. And in some cases, for example, if your database contains financial information, your customers could be exploited if your data is exposed. So we have a safety issue there. Look at all of your assets you need to identify and rank them by criticality. And here we have an example of how you might do that in a particular assets example form, and it has specific assets being the login credentials that various users will have. This continues on to a second page showing you what can someone do with that if they're able to exploit that particular piece of data, that particular asset. Trust levels. No system works without trusting someone or some other system. Your database trusts your application to send it good data, and you trust it to return your good data. So we have to define the access rights, the roles, and the trust levels, not just for end users, but for other systems as well. And here we see an example of this involving users logging in and what sort of trust level do we have, and we have various users and various descriptions depending on which user it is. Now we look at those trust levels and we look at the entry points. Are we having people that can enter in ways that we don't want them to, that have trust levels that are incongruent with the entry points? That's an obvious question to ask at this point. Define those trust levels to assets. Does someone have just the appropriate trust level to access an asset that they should access, and no one is able to access assets beyond their trust level? This is very closely tied to that least privileges concepts we previously discussed. And you can see here there's a whole list of what someone might do if they can exploit a trust level. Now, many of these are things that you're supposed to do for the right person, the trusted person. But an untrusted person doing the same thing is definitely a threat to your application. You may consider data flow diagrams to model your application, and literally they are exactly what the name suggests. They look at any entry points, entities, assets, trust level, and show the flow of data into, through, and back out of your application. This is often a good way to see weak points. Anytime data moves from point A to point B, there's an issue there. There's a potential security problem. When you're doing these data flow diagrams, there are specific diagram elements. You can see here the external entity is represented by a rectangle, multiple processes by 2 circles, a single process by a single circle. You can see data flow, privilege boundaries, and data stores. These are established diagram elements for any data flow diagram that any application developer should understand. And here we see an exemplary data flow diagram, again using that fictitious college library website, and you can see how the data flows from one point to another and in and between users. We follow that through to a deeper, lower level. Now, this is an important part of data flow diagrams. You might start with a very high-level overview of how data flows in general, but you're going to have to get very granular at some point for this to have any meaningful use. Now let's look at the threats. Identify the goal of the attacker and create the threat profile. Who is likely to attack your system? Now you can look at those data flow diagrams and look at the points of possible attack and do a model of who might be exploiting those. Some things can only be exploited by an insider. Well, that's a different threat model than an exterior attacker. That's sort of crude and elementary, just interior versus exterior, but that's a starting point. Here's a few examples of 3 different goals an attacker might have and what vulnerability they would exploit to make these attacks realized, to accomplish their goals. Now you can create a security profile. We know what the attackers are doing. We know what our data flow is. We know our entry points. We know our trust boundaries. We know our assets. Now we can create a profile of all the mitigating controls that our application must have in order to meet these issues. Now notice we're still talking about the design phase, and that's important. We want to identify the security profile and incorporate it into our system design so it then carries throughout the entire system application development lifecycle. Here you see an example of a security profile where we look at 5 different processes here. We're looking at input validation, authentication, authorization, configuration management, and how to handle sensitive data. And you can see the various considerations that impact each of those areas described here. We continue that on to other areas such as session management, cryptography, exception management, and so on. Identify the threats, and they may need to be categorized into different categories. You need to systematically identify the different threats on this application. What are the specific different threats from different parties, different bad actors? And we're going to use something called a STRIDE model that helps us categorize these. STRIDE is a way of looking at various threats, and it breaks them down into spoofing, tampering, repudiation, information disclosure, denial of service, and privilege escalation. Now, each of these have a different property that mitigates them. For example, spoofing is mitigated by authentication. Information disclosure is mitigated by confidentiality, and so forth. Here we're looking at specific threats based on STRIDE. So, for example, denial of service. The threat is aimed to deny access to valid users. Spoofing. The threat action is aimed to illegally access and use another's credentials. So we can see what threats are occurring or possible based on the STRIDE model, which again is spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. Determine the countermeasures, again based on the STRIDE model. For example, if we're concerned about privilege escalation, use limited privileged service accounts. That goes back to the database service account issue I gave you earlier. If you're concerned about spoofing, use strong authentication. Don't send any credentials or store credentials in the clear. Don't pass any sensitive data in the clear. These are methods to avoid the spoofing threat. Document these. What is the specific target? What's the risk? What attack techniques might someone use? What countermeasures do you have? Here you see a template that helps you document specific threats. Rating them. Start with the risks they possess. Prioritize based on risk, and risk is probability times damage potential. Now think about that first one, probability. Not every attack is equally likely. Some attacks are very difficult to accomplish. They require much more skill and time commitment than many attackers are going to have. That makes them a lower probability. On the other hand, they may have a very high damage potential, which would still yield a high risk. There's another model we want to look at, DREAD. Now this is how you rank those threats. Damage potential, that's D. Reproducibility, that's R. Exploitability is E. Affected users is A. And discoverability is D. Essentially, the first one's obvious. How much damage could this threat cause? But the next one gets interesting. Is this a one-off attack that might happen but would be difficult to repeat, or is this something that an attacker can consistently do? Look at exploitability. Could a novice attacker do this, or would it take a top-notch, highly skilled attacker? Affected users. Would this affect a few users, many users, all users? And discoverability. Is this vulnerability well known? We mentioned in a previous module the Open Web Application Security Project Top 10 Vulnerability List. A vulnerability on that list is very discoverable. Most people already know about it. A brand new zero-day vulnerability that has not yet been publicly disclosed would be the opposite end, very low discoverability. And here we have a rating table where we give a numeric rating on each of those areas we just discussed, and that ultimately gives us a total quantifiable numerical value for the ranking of that given threat. And once we've ranked the threats, we obviously start mitigating the most important threats first. So what about designing a secure application? We've looked at threat modeling, we've looked at points of entry and all these different models like STRIDE and DREAD. Well, how do we go about designing it? First of all, security has to be throughout. Simply having security at a single tier is a bad idea. Your web application might be very well locked down, but the database you're talking to should be equally secure. This is that defense in depth principle, making sure every layer has security. Multi-tier applications are very common these days. Well, let's use that to our advantage and have security at each and every tier. Applying multiple layer security in application architecture design is going to make your application a lot more secure. We have a graphic here where we show a client and various levels they have to go through. Each one of these has its own security mechanism. So a bad actor has to go through 3 levels of security to get to that back-end database server, as opposed to simply breaching one and having everything at his fingertips. To summarize what we've talked about in this module, any negligence in security design can lead to terrible vulnerabilities, some of which you may not even be able to detect. And even those you do detect may be very expensive to fix. Secure designing an application is a lot easier if you did security requirements appropriately. You can see how these modules build one upon the other. If you first did good requirements, then design will flow naturally from that. Secure design principles are the state of practices or guidelines which should be enforced on the developers throughout the entire development process. Make sure you understand threat modeling. This may be one of the most important takeaways from this module so that you can identify, analyze, and mitigate threats. Multiple tiered security approach always should be used so at every level we're implementing security.